So yesterday we looked at the graphs of those trig functions as well as talked about transformations. Anybody have any questions? Those graphs are going to be kind of the foundations that we're going to use to develop these other ones. Keep in mind we can use Desmos a lot to kind of reinforce, you know, what we're thinking is going on with these different graphs. So the big focus was, and I'm just going to write it on here, was basically if we have f of x equals a sine of b times x minus h plus k, that was kind of our transfer, we'll call that transformation form. And those values of a, b, h, and k are going to move things around, change the way the graph looks and whatnot. Keep in mind, we could also, I'm not going to write the whole thing over there again, but we could also replace that with cosine, right? And it would still be considered what's called a sinusoid, right? Still what's considered a sinusoid. All right, A is the amplitude, that's a vertical stretch of compression. B is a horizontal stretch of compression, that changes the period. Period gets longer, it's a horizontal stretch. Period gets smaller, it's a horizontal compression. H, we said, was a phase shift. It's going to move things left or right. And K is a vertical shift. That's going to move the entire graph up or down. All right, so I just wanted to highlight those ideas before we get started here. All right, so hearing no questions, we're going to get started into section 5, which, like I said, it's about the other 4 graphs. So students will be able to generate the graphs for tangent, cotangent, secant, cosecant. Those are options on Desmos. Okay. But once again, all 4 of those graphs really come from those 2 we talked about yesterday. All right. Those 2 are the foundations for those. All right. Now, here's what the graph of tangent looks like. And here's why it looks the way it does, and here's why it's being presented this way. Okay. The graph that's in red there, kind of dotted lines, that looks like cosine, doesn't it? From yesterday? All right, so the graph in red should be cosine. All right, so I'm just going to y equals cosine x. That's in red. Now, the way we can develop tangent is that if you remember back when we started using that unit circle, I think we said on that unit circle, didn't we say the sine of any angle was y? And we said the cosine of any angle was x. And the tangent of any angle, wasn't that y over x? Do you remember that? Now, realistically, and this would have made maybe one of the questions on that quiz really easy if you would have put 2 and 2 together here. Some of you did, some of you didn't. Really, wouldn't that mean that tangent of an angle is y over x? It would, wouldn't it? And some of you figured that out, right? That's the last question on the first page. So, the reason the tangent graph looks like this and the reason it has asymptotes is because whenever cosine is 0, tangent doesn't exist. Right? So you can see at these locations, these are the spots where cosine is 0. Tangent has an asymptote. All right? That's why those asymptotes pop up. Because we can't divide by 0. Right? We can't divide by 0. Okay? Now, similarly, and we're going to see this on the next slide, I believe, whenever sine is 0, tangent would be 0, correct? Right? And we're going to see that on the next slide here. All right, but that's why those asymptotes are there. Okay, that's why the graphs, all of these graphs we talked about today are going to have asymptotes. And it's because of that division by 0 idea. Okay? So the asymptotes there, and I think the asymptotes are listed on your little cheat sheet also. Now, the zeros, okay, if you look at this graph, here the one in red is y equals sine x. Well, wherever sine is equal to 0, tangent is also equal to 0. Okay, because once again, tangent is sine of x over, or sine over cosine. We can use x, we can use theta, it doesn't really matter. All right, so that's why the graph looks the way it does. All right, that's why the graph looks the way it does. And we can actually, oops, give me a second here. We can actually go and, kind of graph all three of those. I figured out the problem with Desmos yesterday. I had to put www in front of it. If I wanted to look at all three of those, y equals sine x, y equals cosine x, and once again, this is in radians. And if we look at y equals tangent x, okay, you see those same things. All right, the graph in blue is cosine. So wherever cosine is 0, we have an asymptote, right? I'm using the same color, but oh well, there we go. Right. Similarly, wherever sine is 0, tangent is 0. Right. So having all three of those, maybe that gets confusing, but it kind of shows the reasoning. All right. So let's look at that little trig cheat sheet here. You look at the facts and properties there. Okay. And it looks, if you look at the domain piece, right? For tangent, it says basically the domain of tangent is theta, but it can't be any basically n plus 1/2 times pi. Basically, that's going to be the odd multiples of pi over 2. Okay, right? These points where these asymptotes are all odd multiples of pi over 2, like pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Right? That's how we can state that in words. All right, that's how we can state that in words. All right, so basically that's giving you the locations of those asymptotes. Right? So theta can't be n plus 1/2 pi. Basically, that's odd multiples of pi over 2. Okay. Questions on that? Now, if we can understand that's what cosine looks, or excuse me, that's what tangent looks like, wouldn't cotangent just be cosine over sine? Flip that one upside down? Yeah. Okay, so for the very same reasons as tangent has asymptotes, cotangent has asymptotes, but they're gonna be in different locations. All right? Here, the red graph is, if we go cotangent x, it is cosine x over sine x. All right, so now we have to look here for our asymptotes. Any values that make sine 0, cotangent's undefined. Okay, cotangent is undefined. Now, if you look at your cheat sheet again, cotangent's on there at the bottom. It says theta not equal to n pi. Well, basically that means is the asymptotes of cotangent will show up at any multiple of pi. 1 pi, 2 pi, 3 pi, 4 pi. Okay? That's where those asymptotes will be located. All right? That's what that means. Theta not equal to, so it's defined every value except for those multiples of pi. Right? And the zeros of cotangent would be whenever cosine is 0 because of the reciprocal like that. All right, so tangent and cotangent look very similar to each other. And once again, we can always graph those on Desmos. Okay. Now, just a couple things about those two graphs because they're related, just like sine and cosine are related. These two are related. The period of these two graphs is just pi. We talked about that earlier. The period of tangent is pi. That means the period of cotangent is also pi. All right. One complete cycle of tangent or cotangent is one of these little squiggles here. Okay. It does that over and over again, right? But that's one complete cycle. Right. Another thing to think about is, don't get excuse me, I'm not trying to confuse you with this, but Tangent has no such thing as amplitude. The only two functions that have amplitude are sine and cosine. Think about it. Amplitude was half the length of the wave. Is this wave infinitely long? Yeah, so we can't cut that in half. Right? So we can't cut that in half. Right? There's no such thing as amplitude for this one. Okay? All right. So if we were to, adjust or do a vertical stretch or a vertical compression, that's just going to make that squiggle a little less extreme. Okay, and maybe we'll do that here. All right. To this. All right, so I'm going to go back to Desmos here. All right, so once again, no amplitude there. No amplitude for tangent or cotangent. So if I go y equals, and once again, they're all located right here, cotangent x, you can see it as asymptotes there. Okay. Now, once again, this is not going to be a change in amplitude. This is just going to make that curve steeper, right? Vertical stretch isn't going to make that steeper. Yeah, it almost looks straight, but it's actually not going to be straight. It's just the viewing window we're looking at. Okay. And if I wanted to make it a little more extreme, it would look like that. 0.4, that vertically compress it. Yeah. So no amplitude. It's a vertical stretch of compression for tangent and cotangent. All right. But the period, we still have to think about the period. Period is pi. All right, I want to go back to that. Sorry, I changed my mind. Now, if the period is pi, we can change the period of a tangent or cotangent graph. Y equals tangent x, right? Just as we change the period of those sinusoids, this is going to change the period of tangent. Tangent of 3x. Well, what did that do? That made the period smaller, didn't it? Now, what did we do yesterday? If we had a number like 3, if this was y equals sine of 3x, we'd take 2 pi over 3 to find the new period, right? How's this going to be different here? Well, for tangent and cotangent, we're going to take pi divided by 3. Right? Since it has a different period to begin with, we're going to use the same idea, but if the period of tangent is half as much, we're going to go pi over 3. Okay. So for tangent and cotangent, we would take pi over b. All right, so that made the period smaller. And if I wanted to make the period bigger, whoops, getting ahead of myself here. There I just made the period longer, didn't I? The green one? Okay. Well, that would be pi over 0.2, which is 1/5, which means that would be 5 pi, wouldn't it? 0.2 is 1/5, 2 out of 10. Pi times 5 over 1. Okay. All right, and what would this do? What if I did this? Did I just move it up? Yeah, I just moved it up. Let me get rid of that one. And would this just move it over? I'm gonna go, excuse me, I don't want to go that number. Does that just move it over? All right, so we still have the same transformations. That would be a phase shift of 2. All right, we just moved it over. Excuse me. All right. So once again, remember, we don't have a period. Excuse me, we don't have amplitude for tangent and cotangent. All right, questions so far? All right, so the big things we want to familiarize ourselves with these. Now, secant. Secant is the reciprocal. Oh, geez, got a little cough here. Secant is the reciprocal of cosine. So we kind of use cosine as a guide to graph secant. Right? Secant is what we see in blue there. Well, whenever cosine is 0, we have to have an asymptote, right? So if we look on our cheat sheet, it says what? Theta can't be n plus 1/2 pi. Odd multiples of pi over 2 again. Right. And then we have to remember the idea behind a reciprocal is, you know, if like over here, and I'm not going to be able to do justice with this, but when, like right in here, when cosine is really small, think of a really small number. Would that be like 1/100? Okay, it's a really small number, right? But is the reciprocal of 1/100 really big? Okay, so when cosine is really small, secant's really big. That make sense? Right. Now, the other thing we want to talk about here, once again, no amplitude, but we want to talk about the range. Okay, generally the range of sine and cosine is between -1 and 1. Well, the range for secant is from -infinity to -1, along with, that's not a very good U there, 1 to infinity. All right, it's basically everything but that little gap in there, right? Right. This is 1 to infinity. This is -infinity. Okay. And it's written. It's on your little note sheet too. Okay. All right. So, excuse me. If I'm graphing secant, I generally graph cosine first myself. Okay. And once again, Desmos is easier to graph these. If we wanted to graph these on a graphing calculator, it's more complicated. So Desmos is better, easier to use. Now, that's what secant looks like. You think cosecant is going to look a whole lot different? How is it going to be different? Just moved over? Yeah. Yeah, because it's the reciprocal of sine. And sine and cosine were the same. They just things were just moved over. So this looks like we just took secant and pushed it to the right a little bit, didn't we? So it's going to have the same characteristics. Its range will be from -infinity to -1, along with from 1 to infinity. The period of these two functions is 2 pi, just like the period of their reciprocals. Right? And the asymptotes of cosecant are, they show up when sine is 0. 1/0 is undefined. Right? 1/0 is undefined. Okay? Questions on that? All right, so we want to have a understanding of those graphs. Now this is kind of a summary of these graphs. I know it's really small here, but it's in your book too. Okay? It's kind of a summary of all those characteristics of these graphs. You basically, I think, have most of that on that cheat sheet, right? But it kind of gives you a lot of information. Tells you where the asymptotes are, tells you where the zeros are, tells you the domain, tells you the period. Right? So you're not going to have to memorize this stuff, but you're going to want to make sure you know where to find it. Okay? You want to make sure you know where to find it. All right? Questions? And I think, like I said, this is in the text. It's on page, I think it's in the book. I think it's in the book somewhere, isn't it? Yeah, it's at the bottom of page 364. Okay, but I think a lot of this information is there on your cheat sheet. But if you want to jot it down from the book, that's fine too. Okay. You don't need to memorize, but you should be familiar with some of these things. I mean, you're not going to maybe know them off the top of your head, but you should be familiar with them. All right. Questions? Now, keep in mind, we're not going to look at those functions just plain Jane. We're not going to look at them just, cosecant or just cotangent or just tangent. We're going to look at transformation. So let's look at one together here. I'm just going to make one up, and we're going to work through it. All right, so I think we'll look at two of them. We'll just maybe one, maybe two, we'll see. All right, now, this is how I kind of treat some of these, so you don't have to do it my way, but this is how I'm going to describe it. All right, now, if I was going to graph that, this is just me, you don't have to do it the way I do it, right? I would first start with graphing this. Because would those be the reciprocals of each other? Yes. Okay. And we talked about that yesterday. So I'm going to graph that one up here, and you're going to help me. All right. That's going to be a graph of cosine, but how is it going to be different than the parent? How is it going to be different than basic cosine? Two ways it's going to be different. What's one? What is this going to do? We're going to have an amplitude of 3, or vertical stretch, right? What is this going to do? Okay, so this is the this is going to affect the amplitude. What's this going to affect? The period. So the period is going to be 2 pi over 2. It's going to be smaller. I heard someone say smaller. Yeah, it's going to be half as much, right? That's kind of reviewing what we talked about yesterday a little bit, right? So if I graph that, okay, and this isn't going to be perfect because this is freehand here. It might look something like this, right? That's the graph right here, right? Now, furthermore, I would probably know that this is pi, because from 0 to pi would be one complete cycle. That's my thinking, right? We said the period was pi. This would be 3, and down here, this would be -3. Is everybody okay with that? Need me to explain how I came up with that? I'm using what we had here. The period was pi, so from peak to peak would be pi radians. And the peak is at 3, and the bottoming out is at -3. Okay. Right. Now, the nice thing about, and maybe you don't think it's nice, but I do. The nice thing about these trig functions is there's some kind of balance here. Where would this be, this low point? Wouldn't that have to be kind of halfway between 0 and pi? And what would that be? Pi over 2. And then technically, wouldn't these be kind of halfway in between those other two? All right, what's half of a half? A fourth, right? Right? And then this would be 3 pi over 4. Right? So there's some balance to these. I mean, we can find those numbers if we split things in half. Now, the reason I found those is because, and I'm going to go over here. Do you think this would be -pi over 4 right here? Now, the reason I found those would be, and you don't have to always do this by hand, but I am. Would those be my asymptotes for secant? They would, wouldn't they? Whenever cosine 0, secant is undefined. Okay, and then to graph that, if we're doing it by hand, it's going to look like this. Technically, there'd be another asymptote there. All right, now that's not pretty, but it's a rough idea of what that graph would look like. The graph of secant is the one in blue. Right? That's how if I'm doing this by hand, that's how I'm going to graph that function. I use cosine as a guide. Can you see why I use it as a guide? Because once we got cosine figured out, we'll see anything. Yes. Okay. That's my reasoning behind that. Okay. Notice when the period changed, did that change the asymptotes? Basically the asymptotes are normally odd multiples of pi over 2. Are they closer together now? That's odd multiples of pi over 4. Half compressed it by 2, a factor of 2. Okay, so everything is going to change accordingly if we change the period. Questions there? All right, how would it look different if I did this? What if I added that plus 2 at the end? Just move the whole thing up 2. Just move the whole thing up 2. That's all it would do. All right, so a big focus of Algebra 2 last year was transformations, wasn't it? We're using a lot of that thinking right now. All right, we're using a lot of that thinking right now. All right, anybody have any questions? All right, I'm gonna give you some questions to work on for Monday. A lot of it will be familiarizing yourselves with those graphs. We talk about a lot of the characteristics. I'm gonna put some of that to work. Questions to work on for Monday. Remember, Monday we'll take a step back and we will spend more time looking at these graphs on a worksheet. Yep. Yes.